So this video is about Markov chains. In Markov chains, usually I have states and I'm moving from a state to another where the moves are independent from each other. When I have a Markov chain, I can represent it with a matrix or I can represent it with a graph. So for example, if I have a graph with states S1, S2, S3, and I move from, let's say, from S1 to S2 with a probability, whatever, 1/3. I can move from S2 to S3 from a probability 1/3. I can also move from S1, and I can stay in S1 with a probability 2/3. So the arrows that goes out from a node will sum up to 1. So, and then here, like I can go back with probability of 1/3, and I can stay here with a probability 1/3, and here I can go back with a probability 2/3, let's say. So what the meaning of that the moves are independent from each other, it means that once I move from S1 to S2, I have a probability of 1/3. Then my next move will be independent from the one before. It means that I will keep the same graph. So the probabilities will not change from a move to another. Now, a Markov chain can also be represented by a transition matrix. And the transition matrix is a square matrix that has all the states, the probabilities from moving from a state to another. So it's an n by n matrix if I have n states. And then let's call them P11, P12, P1n, P21, P22, P2n, Pn1, Pnn. What is the meaning of each value? So Pij is the probability of moving from state I to state j. So it's probability of moving from state I to state j. So for example, the corresponding probability transition matrix for this one, I have 3 states, 1, 2, 3, 1, 2, 3, or S1, S2, S3. The probability of going from 1 to 1, which is this loop, is 2/3. The probability of going from 1 to 2 is 1/3. And there is no probability for going from 1 to 3. Now, from 2 to 1 is 1/3. From 2 to 2 is 1/3, and here is 1/3. 3 to 1 is 0. 3 to 2 is 2/3. Okay, I need something here. 1/3. So the sum of each line is equal to 1. So this will sum up to 1. Same here, the same here. So 2/3 plus 1/3 is 3/3, which is 1. And here, so the sum of each line is 1. The columns are not important. Now, if I have a transition matrix, that usually I call it P. I can also, if I want, so this will give me probability of moving from S1 to S2, for example, in only one step. So when I say here that I cannot go from S1 to S3, I mean that I cannot go in one step, but I can go from 2 steps, right? I can go from S1 to S2 and then from S2 to S3. And to find the probability of going from a state to another after n steps, I have to, after k steps, I have to compute pk. So p to the power k gives me the probability matrix of moving from a state to another in k steps. So usually you don't really need to compute the whole power of the matrix. If I want to find the probability of going from S1 to S2 in 2 steps, I can compute P2, and then once I have P2, I will go from 1 to 2 in 2 steps. So I will look at this value in P2. I have P2. No. Anyway, or I can just see it on the graph. If I want to go from S1 to S2 in 2 steps, I can check all the possibilities. But if you can compute the element of P2, so I can take this matrix times this matrix, and then I can compute only the element that is on the first row on the second column, then you know that you will not miss anything. Or on the graph, I know that if I want to go from S1 to S2 in 2 steps, either I go S1, S1, S2, or S2, S2, S2. Okay, and then I can take the sum of their probabilities. Another type of Markov chains, or a special type of Markov chains, is if my matrix is strictly positive, or some certain power of the matrix is strictly positive, it means that all the elements are strictly greater than 0. So here it's not the case. P is not strictly positive, but maybe if I compute P squared, then it will be strictly positive. Then I say that my probability matrix is, my Markov chain is regular, and it means that when I take K, K goes to infinity, it will tend to be the same matrix. So the limit of this P to the power K is equal to one specific matrix. That gives me all the probabilities. P is regular. P to the power K has 3. So if all the elements, if there exists K, such that all the elements of P to the power K are strictly positive. The strictly is important, because if you just say positive or equal to 0, this is not true, because all the Markov chains, they will always have greater or equal to 0 elements, because they are probability. In this case, if P is regular, then P to the power K will tend to, as K goes to infinity, to a matrix Q, which has the form Q1, Q2, Qn, Q1, Q2, Qn, Q1, Q2, Qn. So it's the same column. And so it means that whatever state I start with, I will always end up in a state with the same probability. So this like Q to the power, Qj is the probability and end up at state J, independently from the starting point. Independently of the starting states. And it will always be together. It will always be the same starting states. Okay? This is the first type of Markov chains, the regular one. And then we will see also the absorbing Markov chain. So absorb. Markov. So a Markov chain is said to be absorbing Markov chain if it has absorbing states. An absorbing state is a state that once you get into it, so you will not be able to leave it. So the probability of staying in this state is equal to 1. So absorbing state state that one can never leave, like when someone dies. Yeah, okay, no jokes about this. So the transition matrix of an absorbing Markov chain is equal to, it can be the canonical matrix, it can be written in this form, QRI0. I is an identity matrix, okay? And here I will put the absorbing states. So I can rewrite my matrix in order to get identity. So the one should be on the diagonal. And these will be the absorbing states here and here. And Q is a matrix that gives me probability of going from a state that is not absorbing state to a state that is not absorbing. And the non-absorbing states are called transient states. Now, and R is a matrix that gives me probability of going from a non-absorbing state to an absorbing state. So P to the power n is always equal to Q to the power n times a certain matrix I and 0. 0 is not an element 0, it's the matrix 0. Now, if I have an absorbing Markov chain, I can compute the matrix n, which is the inverse of this matrix. So this matrix, it gives me the expected value of the number of moves that I need to do if I start from a state Sj in order to be absorbed in another state Si. So if this matrix is equal to, it's a square matrix. So if it's let's say S1, S1 SR, S1 SR. If I take a number here, I will get the expected value of moves in to be absorbed if I start from S1, and before I get absorbed, I will also be at S1. And here it's like I start at S1, and then I get to SR, and then I get absorbed. And the average value of this, the number of moves in order to get this will be this value. Now, when I take n and I multiply it by a column vector of ones of corresponding size, then I get a matrix that gives me, I get a column matrix that gives me, let's say here I have n1, n2, etc. This n2 is the average number of moves to be absorbed if we start from state 2, sorry. If we start at state 2. I think I was muted the last here. I will repeat it. So this matrix, n times r, it gives me a probability matrix that tells me that, for example, if I start here, if I have the state S1, and here, so here I will have the transient states, and here I will have the absorbing states. So this value, it will give me the probability of being absorbed in this state, knowing that I started in this state. This will give me a probability of being absorbed in this state, knowing that I started in this state, and etc. And this is everything about Markov chain. And the next video, it will be about estimation. So it's going to be descriptive statistics.